Next, we're going to talk about the derivative of a function. So the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations in calculus, and that is differentiation, which is the process of finding the derivative. So let's look at the limit definition of the derivative of a function. So the derivative of a function f is given by f prime of x equals the limit as delta x goes to 0 of our difference quotient. And this is exactly what we're looking at. So by finding the slope of the tangent line, you're actually finding the derivative. And note, this can be a function, like we just found. Now some other notations for the derivative. We have f prime of x. We have dy over dx, which is the derivative of y with respect to x. We can also write y prime, or we can notate it this way. The derivative of f of x with respect to x. So those are four different ways that you're going to see the derivative written. Now this right here is the alternate form of the derivative. And this is going to be used when asked for slope or for derivative at a specific point. Okay, so derivative equals slope, and we're going to just equate those two from here on out. So our first example says find the derivative of f of x equals 4x squared plus 5. So here's how we're going to do it. We got f prime of x, and it equals, well, here's our definition, the limit as delta x goes to 0. Okay. Notice we don't have a c here. So we're just going to be using this equation, and what you want to do first is take x plus delta x and substitute it right in there for your x's. So we have 4 times x plus delta x squared plus 5. So remember, that's our first f. Then minus our second f, which is just f of x, and all we have to do is rewrite the function. 4x squared plus 5. And all this is divided by delta x. So setting this up is probably the most difficult part, and now it just becomes algebra to simplify this thing. So first we're going to multiply the binomial here. We can distribute our negative. Okay, now we're going to distribute our 4. Now watch as the constants and any terms with only x disappear. So we have our 4x squared here and a negative 4x squared here. So those are gone. We have a plus 5 and a minus 5. Those are gone. And we're left with only terms that include delta x. Okay. So this is good now, because we can factor out that delta x in the numerator. So we have the limit still. So here we factor out the delta x, and we're still left with 8x plus 4 delta x over delta x. Delta x's are going to cancel. This limit keeps tagging along all the way to the end until finally we can use direct substitution here. So we're going to put 0 in for delta x, and we're left with 8x. So we can write f prime of x, which is the derivative, equals 8x. So from here, they might ask you to find some things. You might be asked to find f prime of negative 2. Well, if we look at this, f prime of x is our function for the derivative. So all we have to do is substitute negative 2 in for x in the equation here. So this is going to equal 8 times negative 2, which is negative 16. Now what this is telling me is this function right here at negative 2 has a slope of negative 16. What they also might have you do is find the equation of the tangent line at x equals negative 2. So again, you just need a slope. We found that was negative 16. Why is the slope negative 16 if the derivative is negative 16? Because the derivative equals slope. All right, and it's when x equals negative 2. So when x equals negative 2, what does y equal? So we're actually going to have to take our original function, the 4x squared plus 5, and we're going to substitute 2 in there. So we've got 4 times negative 2 squared plus 5. And that gives us 4 times 4, which is 16, plus 5 is 21. So you might have to find the point. So remember, you need a slope and a point. Now we can use point-slope form. And simplify. And if we add the 21 over, we get y equals negative 16x minus 11. All right, let's move on. In our next example, it says use the alternate form of the derivative to find the slope of f at c, okay, of f of x equals x squared plus 1 at x equals c. We're going to make this at c equals 2. Okay, so for this one, we're going to use the alternate form of the derivative here. The limit as x goes to c of f of x minus f of c over x minus c. So it's just a different way of looking at this. So f prime of x is going to equal the limit as x goes to 2 of f of x. So that's just x squared plus 1, and we're still going to use our square brackets, minus f of c, which is 2 squared plus 1. And then this is going to be over x minus c, which is x minus 2. So notice direct substitution still fails. So we're going to have to continue to work with this until we can cancel out the x minus 2. So nothing we can do with f of x. We just leave it x squared plus 1. This becomes minus 4 minus 1. That becomes minus 5. So you have x squared, or actually you can just look here, plus 1 minus 1, and just get minus 4. And now we're left with a very nice function in the numerator that we can factor. So difference of squares, x plus 2, x minus 2. You can see we cancel out our factor. And now we can use direct substitution. And so we get 4. All right, now the next question here says find the equation of the tangent line at x equals 2. So again, our m equals 4. We need to find our point where x equals 2. So let's do our function x squared plus 1. So 2 squared plus 1 is 5. So it's the 0.25. And you can use point slope form. And there we have it. I want you to take this time now and go through this process of finding the derivative. And I want you to explain in your own words how to go about doing this. All right, moving on. Next, I want you to try these two examples here. So you might want to pause the video, give that a try, and then come back and check your work. All right, welcome back. Go ahead and take some time and go through these and be ready to have those questions in class, but really try to figure out the steps and compare it with what you've done. All right, so I'm just going to pause the video and check your work. All right, and last couple things won't take very long and we'll be done. One thing that's true is that differentiability implies continuity. So if f is differentiable at x equals c, then we know f is continuous at c. And so if you can find the derivative at c, then you also know that it's continuous at c. Anyway, moving on. We want to just think about this, and we want to tell where f prime of x is positive, negative, 0, or the derivative does not exist. So let me give you some functions here. Okay, so in this function, we're just going to mark it up like this. So right here, the derivative, remember the derivative is the slope of the graph. So here it looks like the slope of the graph is positive, positive. Okay, it's still positive until we get to right here, and it's flat. And so here the derivative would be 0. After this point, notice these would all have negative slopes. Okay, let me give you one to try here. I want you to mark this up just like I did right here. Pause the video, come back and check your work. All right, so you can see here we have a positive slope right here, 0. Then we switch to negative slope, 0, and then positive slope. I'm going to give you one that looks like this. Okay, so as we come here, our slope is positive. And one other note, since it's a straight line, the slope is going to be constant here. And what happens here is, because there's a sharp turn in the graph, there is not going to be a derivative here. So it does not exist. And that's what this little box is telling us here. So there's not going to be a derivative where the graph is not continuous, like a hole or a vertical asymptote, or where the graph has a sharp turn, like here, or where the graph has a vertical tangent line. Okay, so finishing this out, it would be negative right there. All right, let's try this graph. So where is it positive? Where is it negative? We have a vertical asymptote there at x equals 0. So here the slope is going down. So we got negative. Right here at 0, it would not exist because of the asymptote. And here, it's also always negative. So the slope of this function is always negative. Let's try another one. So here we have a stepwise function. So what is the slope of this line? Well, it's flat. So the slope here is 0 all the way along this line. Here we have a break, so we have a discontinuity. So the derivative does not exist. And then it continues on with the slope of 0. And one last one. Okay. So here we have increasing, increasing, increasing becomes vertical. So right at this point, it would not exist. And notice the slope is still increasing. All right. That is it for our derivatives. Please, again, record any questions or comments and bring those to class. And I look forward to seeing you then. Thanks for watching. See you later.